real numbers. They're giving you the derivative and they want to know where it is decreasing. So this is to the point that I've been trying to make, the whole year when it comes to increasing and decreasing is you care about positive or negative. So it's decreasing when the derivative is negative. The numerator is always positive because of the absolute value.
Okay.
The bottom is negative depending on where you are on the 3. If you're right of 3, it's positive, but if you're left of 3, it's negative. Like if it's 2, 2 minus 3 is negative. If it's 4, 4 minus 3 is positive.
Okay.
So that's the only scenario where you get a negative derivative. So from minus infinity to 3.
Okay. So you just solved the bottom for, you just solved it for, well, you set it equal to 0, right? To get 3.
Yeah. The top is, so I mean, it's not entirely true because at negative 3, it's neither increasing nor decreasing, but your answer space doesn't include that because that's where the top is 0 also, but that's where the 3 came from.
Okay.
All right, I'm gonna go on to 14 now. Okay, let f be differentiable such that f of 5 equals 3 and f prime of 5 equals 2. Okay, so see here. Okay, and if the tangent line to the graph at 5 is used to find an approximation to a 0 of f, that approximation is a lot of words.
Yeah.
So let me just try to graph what's here. When x is 5, y is 3. So here is 1, 2, 3, 4, 5, and then there's 3. So that's the point. And it's saying it has a slope of 2. So you can see here that like we don't know what the curve, we actually have no idea what the curve does, but let's just say that that's what it is. That is the tangent line right there. That's 5, 3. This has a slope of 2 over 1. And so they're like basically saying, well, where does it hit the x-axis? Like, well, somewhere down here. So we would say roughly midway between 3 and 4, 3.5 maybe.
Okay.
If you would like, I could probably make one up like this if you want to try. This one's not too bad to figure out.
How did you find the 2? I don't.
So this is the slope. This is the slope of the tangent line. Because they're telling you the derivative at that point.
They're asking you to find the wait, so they're asking you to find a zero?
Yeah, it's really weird, isn't it?
And so the 0 would be what?
3.5 here. This is such a weird, it's worded really, there's what they should be saying is, where does the tangent line intersect the x-axis?
Okay.
But they're saying it in an odd way. They're saying use the tangent line because the tangent line approximates the 0 of the function. So instead of using the function, use the tangent line to figure out where it hits.
So there's no other way to do this other than graphing?
Well, you don't. The graph was just to help. You literally just have to find the equation of the tangent line and set it equal to 0. So the equation of the tangent line is y minus 3 equals 2x minus 5. So it's y equals 2x minus 10 plus 3. And then you set that equal to 0.
Oh.
I thought the graph out like we don't, they're suggesting, and maybe this is the problem is that this thing is drawn so poorly. They're suggesting that there's like a crossing here. This is f. And they're saying, oh, that's the tangent line right there. And then so that, see how the tangent line's pretty close to where it actually hits?
Yeah.
That's what they're trying to suggest or get you to see.
Okay. But they give you everything that you need for the to like write the tangent line out though.
Exactly, because you need two things for a tangent line. You need a point and a slope.
Mm-hmm. Okay, so
I wouldn't overly, I think it'd be good to move on. Unless there's.
yeah, no, I mean it's yeah. Let's just move on.
Okay.
It makes sense. It's just like a weird problem.
Yes. Would you like us to go to 17, or is there some other ones that we skipped that you think would be worth doing?
Don't remember. I know we did 6. I think those are the only ones that we skipped, if I remember.
Okay.
So we can just go to 17.
Let's go to 17. All right, just snipping it in here. Okay, so they give you this this equation. They want you to find the second derivative at a specific point. So that means the answer is a number, as you can see by the answer space. So when you're doing implicit derivatives, you have to remember a few rules. The first is with x, you just treat it like you always do. Constant 0. Now the derivative of this right here on the right is it's minus 2y, but there's a dy dx.
Okay.
When you're doing implicit derivatives. Now we're just going to clean this up slightly. It's 2x equals minus 2y dy dx. And there's kind of a minor thing here that's probably worth doing. We actually should probably divide both sides by minus 2. And I'll show you that in a moment here, why, or try to give you a better explanation for that in a moment. But
okay.
So now we need the second derivative. Okay. We're going to take a derivative of this line again here, but we're going to do it off on the right hand side here. So the derivative of x is power rule, just -1. This on the right is product rule. This is a product on the right. It's y times.
Yeah, y
d2y over dx squared plus
y prime dy dx.
Yeah, so it's actually dy dx times dy dx. And so here's how it looks when I clean this up just a tiny bit here.
Because y prime is dy dx?
That's right.
Okay.
So you end up just squaring it.
Okay.
All right. Now, it wants d squared y dx squared. It wants this thing over here on the right. Your dy dx you can get from over here if you solve for dy dx. So what you have to remember here in this problem is you don't want to solve for dy dx. You want to actually leave it in this form and then take a second derivative kind of off to the side. Otherwise, it gets very messy if you don't do it this way. So dy dx is minus x over y. That's what goes here, minus x over y squared. -1 equals y d squared y over dx squared. This is probably the point where I would plug in numbers. X is 3 and y is 4. These are given. So -1 equals 4 d squared y over dx squared. So plus -3 over 4 squared. So that's 9 over 16. Maybe subtract that over multiply. So I guess we'll subtract this. This is -16 over 16. -9 over 16 gives you -25 over 16. It's 4. d squared y over dx squared, divide by 4. So it's minus 25 over 64. Hopefully that's right.
So
Yeah.
they're just asking you to find dy or d.
The second derivative, yeah.
Okay.
Yeah.
Okay.
All right, moving on. I guess I could make, I can always make some up, but there's so much work on that one. I probably would suggest we move on. All right, to number 18. All right, number 18.
Okay, so you have to do an antiderivative, right?
Yes. This is a U substitution though, because there's no known like, yeah, this is it.
So
There's
is,
all, oh, go ahead.
so is the u typically like the exponent or the thing on the bottom? I just forget.
Exponent, parentheses, the root, under the root, the denominator, lots of things that it could be.
Okay.
It's trial and error, which guess and check. There is a small thing that I think you could do here to make this better, which is a rewrite step. I'll show you that. So 1 over sine squared is cosecant squared x.
Mm-hmm.
And that might help. So your u, the other thing you're looking for with your u is its derivative must be in the problem in some way. So do you remember the derivative of cotangent? Do you remember the derivative of tangent?
Yeah, so squared x.
So this is minus
Oh,
cosecant squared x.
yeah.
And that's why this rewrite is so important, because you may not notice what to do if you leave sine squared on the bottom, but now that it's here, it's like, oh, well, I think I can do this. You have a choice, whether you want to evaluate the endpoints. I don't really love cotangent as a thing to evaluate the endpoints at, so I might save it. Not sure.
We'll see to rewrite with the u and stuff now, right?
Yeah, so this is minus cosecant squared x e to the u du over minus cosecant squared x. And what I was referencing is like, do we want to figure out what cotangent of pi over 4 is? And do we want to figure out what cotangent of pi over 2 is? Because that will change the bounds.
Well, don't you need to find out what they are?
You can do this part, find the antiderivative, then back substitute. So I guess I guess by that point you actually do have to figure these out. So you might as well do it now.
Okay.
So what I would prefer doing is doing this as 1 over tangent pi over 4. I think that would be potentially easier.
So root 2 over 2. No, wait. 1.
It is. It's root 2 over 2, like you said, over root 2 over 2, which is 1.
Right.
And then cotangent 1 over tangent pi over 2. So sine pi over 2 is
Sine pi over 2. 1/2 is a half. No.
it's a 0, or it's 1 over 0.
Oh, that's the top one. Yeah, because it's pi. Okay.
It's 1 over it, so it ends up being 0.
Okay, so then it's
so pi over 4 is 1 to 0, like that.
oh, that's where you change it. Okay.
Yeah, you change it right there. These cosecant squareds cancel. That's why this problem is here, because if you do this correctly, you get a really nice integral, which is just itself. So it's e to the 1 minus e to the 0, which is e minus 1.
Huh. Okay.
I think I gave you the wrong derivative. I think it's just cosecant squared also. Because the answer is 1 minus e, which, but let me check. I should know this, but you'd be surprised how quickly you'll forget this stuff if you don't use it every day. No, I guess it is. I guess it is minus. All right. It shows the answer as being 1 minus e. So I don't know. We could look into. We could. That's probably should just move on.
Can we do like a simpler u substitution? Because I feel like I'm still
Yes.
not great with it.
Let's go integral 2x e to the x squared 0 to 1 dx.
Okay, so your u is x squared.
Yes.
Your du would be 2x dx. And then your dx is 2x. Wait. 2x. No, du over 2x is there. I mean, du over 2x is your dx, right?
Yes.
Okay.
That sounds right. U equals x squared du. Yes. Dx is du over 2x.
So then it's 2x e to the u at 1 and 0. So that's 2 to the 1. E to the, wait, what did you do? Oh, okay. Those cancel. E to the 1 is 0. E to the 0 is, wait, is e to the 1 0?
It's e. Yeah, e to the 1 is itself.
Oh. E to the 1 minus 1. So then that's all you can do, right?
That's right.
Okay.
Is that okay, or do you want another one?
That makes sense. We can move
Okay.
on.
All right. Number 19. I remember we did 20 already. It's amazing how the brain works. I haven't seen this since the last time we looked at it. And I know for sure we did 20 because I remember saying, let me find one that's short, and it was. All right, so this one is asking for the derivative of ln. So d dx natural log of u. U refers to whatever's inside parentheses. It's always
1, well, ln is 1 over x, right?
yeah, or 1 over u, and then you take the derivative of the inside function. So it's 1 over 1 minus x squared, but then you multiply by the derivative in the numerator.
Oh, okay. So, oh, so
That's it. Now, let me give you one that's slightly more interesting, potentially. Let's say it's natural log absolute value of sine x.
Okay, so it'd be 1 over sine x, and then the top is times cosine x, then cosine x over sine x. Well, sine x over cosine x is tangent.
Yeah, so what is cosine over sine?
1 over tangent.
Yes, that's true. That's true. What is that? Cotangent.
1 over, oh, yeah.
So this answer would not be there, would be there, would be there.
Okay.
Is my guess.
1 over tangent is cotangent. Okay.
All right. Have you thought about how much different college will be compared to what you've been doing the last few years?
I have. I'm so excited to not be in high school anymore.
Yeah, it's a different world altogether. All right. Yeah, so new question here. I think one of the things that escapes students is that you do always try the number.
Right. So
and if it works, like
ln1.
So the natural log of 1 is always 0.
So 0.
0. So this is an awful question. So let's make it better. I can't believe it. So let's find the limit as x approaches
because
1.
that's just the.
Yeah, that's the answer.
So if it wouldn't, what, like,
that's what I want to give you here, because it's
okay.
this is a terrible question the way it's written, because it's good in the sense that, yeah, you just plug it in, but I don't think that was what was intended. But so how about this one? It's natural log of 1 over 3 times 1 minus 1, which is 0 over 0. What is that?
L'Hopital's rule?
Yes, it's indeterminate form. So in this case, you have to take a derivative of the top and a derivative of the bottom.
So, like, what is an example of one that would, like, if you plug it in, it wouldn't work? That's that one that you just gave?
Yes. And I think that was what was intended.
How do you know that it doesn't work? Like, because you got 0. Like, why does that not work?
Oh, it does work. That's the answer. But it's
no, like for the bottom one. For that one.
Oh, because you get 0 over 0. That's one of the indeterminate forms. There's a couple of indeterminate forms, like infinity over infinity.
Right. So if you get one of those, you know that your answer is not like 0. Basically, it can't be 0. That just means
you have to keep going. It could be 0. You have to keep going.
Okay.
So do you remember L'Hopital's rule? I kind of started here. It's separate derivatives. So you take derivative of 1 over natural log 1 over x. And then what is the derivative of the bottom?
Should you multiply out the 3 or like distribute?
Yeah, probably good to do that. So it's 3x minus 3. So it's not product rule. It's just
3.
Yes. And you have a choice. You can actually simplify this, or you can just go back and put 1 in again. So 1 over 1 over 3, which is 1/3.
Huh. Okay. So the only other, so if you can't plug it in, like just directly like we did at the beginning,
yes,
the only other option is like L'Hopital's rule, or there's other things.
There's other cases where it goes to infinity. So let me let's think of a graph that does that. Like, this is not a great example, but limit as x approaches 0, 1 over x squared. So the graph of 1 over x squared looks like this. Okay. So when you put 0 in, you get 1 over 0. That is not indeterminate form.
Right, because you can't divide by 0.
So you don't use L'Hopital's rule. You just have to like be like, oh, it goes to infinity. More often than not, you're going to get this kind of example I just gave you, or I guess the previous one, where just.
Can we do one more L'Hopital's rule?
Sure. Yeah. Limit x goes to 0, sine x over x.
Okay. So we got to test it, sine of 0 over 0. Yeah, so 0 to 0. And then cosine x over 1. So then cosine 0 is 1. 1?
So you take the derivative of both top and bottom, right?
Yeah.
Cosine x over 1, and then you try it again because you get 0 over 0 in this. So yeah, it gives you 1.
Okay, cool.
We didn't do one that was like infinity over infinity, but that's the other indeterminate form that you're possibly going to see.
So if it was infinity over infinity,
You do this, you just keep taking derivatives.
but like, how would you know that it's infinity? Like, it's just it's a number that.
So it happens more like this. Limit as x goes to infinity, x cubed over 5x cubed.
Oh, so it's like infinity to the third. Okay.
It's infinity over infinity. This is a bad example, but because you might already know that it's 1/5, but you would just keep taking derivatives of the top and the bottom.
Oh, it's 1/5 because the exponents are the same.
Yes, yes, but you can prove it. You can prove it with this.
Got it.
Or show it. All right, is moving on to 22. Is that good?
Yep, sure.
Okay. What are all the values of x for which the function is increasing? So this is the original function. For increasing, decreasing, you need the derivative. Excuse me. What is the derivative rule that you're going to use here?
Product.
Product rule.
So x squared minus 15 times e to the. Oh, it's negative e to the x. I mean,
yes, yes, because you're using the chain rule as part of the product rule to take the derivative of e to the minus x.
Okay. 2x times. So then you.
So if you've gotten to this point right here, this is the hard part. You set this equal to 0, but you have to actually factor stuff out. So if you factor out an e to the minus x from both of these, this negative goes with these here. So it's minus x squared plus 15 plus 2x. And then I would probably factor the negative out. I probably should have done that from the beginning. So it's x squared minus 2x minus 15.
And then set the, okay, so then 3 and 5, yeah. So then x equals 5, negative 3, and then you have the e to the negative e to the negative x. So you set that equal to 0. How do you solve that part?
So x is 5 and x is -3 are your two possibilities.
Right. What about the negative e to the negative x though?
This is never equal to 0. So the graph of e to the x looks like this, e to the -x looks like this, and then the negative out in front just flips it. But it's never 0, never crosses. So that's always positive. So you just test points in each of the windows. You get positive, negative, positive when you do that.
And you test that in
the derivative, but that's always positive. So you can just test the factored form.
What do you mean?
I'm sorry.
Positive.
I'm sorry. I have this totally wrong. This is always negative. So I've got these reversed. Sorry, let's actually test some points. So you can see this. Sorry, I'm just jumping around too quickly. So if we plug in, say 6 is over here. 6 minus 5 is 1. 6 plus 3 is 9. That's positive. So it's a positive times a positive, but the outside one is always negative because of the negative out in front. It's e to the -6, but it's negative.
Oh, I see.
This is a negative, yeah.
So then you can test like 0. So 0
Yes,
minus
test 0 is, yeah, so 0 minus 5, negative, positive, that's negative. Even though it's e to the 0, it's still 1, but it's negative.
And then like -4. So -4 minus 5, that's negative. -4 plus 3, negative. Negative, negative, negative is negative.
Yes. And it's this one will end up being a negative.
Right.
So now it says, where is it increasing? Well, it's increasing in here from -3 to 5.
Okay.
Right. 23 look at next. Is that good? Are you planning to do all the sort of like first semester questions, derivative questions first, then the second semester, integrals first, or just go in order? What's your strategy?
I usually just go in order, honestly, but then I like skip around if I don't know the question. I don't really try to separate it.
Yeah, because from the previous one to this one, it's totally different parts of the course.
Right.
Okay, so it says if the region enclosed by the y-axis and the line y equals 2 and the curve y equals cube root x is revolved around the y-axis, that's important. So the picture is kind of useful here. Here's 2. And then you maybe wonder, why am I going out so far? 1, 2, 3, 4, 5, 6, 7, 8. When x is 8, y is the cube root of 8, which is 2. That's how we know where they hit. So this cube root of x has sort of this shape to it like that.
Mm-hmm.
So you get this kind of right here. And they want the region. They want the air. Oh, no, I'm sorry. They want the volume of the solid. So y-axis.
Wait, sorry. How did you get the x equals 8?
Just knowing we want y equals 2. So you set 2 equal to y, cube root of x. So I just, instead of cubing both sides, I just worked it backwards, but 8 is x.
Got it. Okay.
So, the bad part is you got to go around this axis. When you're doing y-axis integrals, you have some choices. You can either do it with respect to y and use the disk or the washer method, which is probably what you'll end up doing. You probably end up doing a disk here, but you could also use the shell method, and then it's an integral in x. But
so
I guess
disk is when what's the difference between disk and washer again?
So I think of disk as like a pancake. There's no hole in the center, and then washer is when there's a hole in the center, when there's like a gap between your region and the axis. So this is a disk because there's no gap between your curve. So
And that's which axis though? X.
the y. If it were x-axis, it would be a washer because there's a
Got it.
disk.
So, but it's because it says it revolved around the y-axis.
Yeah.
Okay.
Okay, now we're doing it with respect to y, so you need the y coordinates here, 0 to 2, and it's pi r squared. So your r, let me do this in a different color. Your r is the distance from your axis to the curve. And your curve here, you have to solve for x. X is y cubed. You're solving this thing right here for x.
Okay.
So that is your radius. Your radius is this y cubed squared. It's pi integral r squared dy.
Y cubed square. So you just got that from.
Because when you're going about the y-axis, you have to solve for x. Because all the equations are flipped. You know, x. It's in terms of.
Oh, so you just cubed
Both sides.
Okay,
Yes.
okay. So then you do the antiderivative of that, and then.
Well, yeah, I would square it so you get y to the 6th, and then yes, antiderivative 1/7 y to the 7th, 0 to 2 times pi.
Y to the 7. Okay, so then it's.
So 2 to the 7th, 2 to the 6th is 64. So 2 to the 7th is 128.
Over 7.
Yeah.
128. Does 7 go to 128?
No.
Okay. So you just leave it like that. Or no? Yeah.
Yeah, that's it.
Okay.
The divisible rule for 7 is I think you subtract the digits. You get 8 minus 1. Then you add, and and then you divide, and it doesn't work out. This one definitely doesn't.
Okay.
Okay. We have some time left here. Do you want us to just keep going in order? Do you want to maybe look and say, do these?
Yeah, let me look real quick. Oh, Riemann sum would be good to do. Okay, I think definitely the next one, and then we can skip a little. Maybe to 27, and then 28.
Sure. Let me step it in.
Or maybe we could just do like one that I have to find the Riemann sum for. I don't know. Would that be easier?
Yeah. I mean, this is what I was gonna say. You need to know these things, and there's apparently 30 n's because it goes from 1 to 30. So n is 30. It starts at 1. A is 1. B is 30. That doesn't seem right. Oh, I'm sorry. It starts at 0. So this is a right sum because if you remember, we said write all the numbers out, so on all the way up to 30. But then if you start at 1, you use that. But why is there a 30 in the bottom? Huh.
Should we just do
Yeah, maybe we'll pick one. Let's just pick. Do you think B is correct? Because it's not circled in the other color. So yeah, I guess it is. So let's go 0 to 1, sine 30. Sorry, sine x dx. And let's say n equals 30. So your delta x is b minus a over n, 1 minus 0 over 30. That gets you the 130. So your Riemann sum is 1 over 30 times. And then you're evaluating this, but you got to know whether it's a right or a left sum. And that's one of the things that they didn't make clear here. Since you're starting at 0, it's 0, 1 over 30, 2 over 30, 3 over 30, and so on, all the way up to 30 over 30. So if you notice in your problem how it starts at 1 over 30, they're saying that it's a right sum, so use the right numbers. So you plug each of these numbers back in for x. So sine 1 over 30 plus sine 2 over 30 plus sine 3 over 30, and so on.
Mhm.
It's very hard to work backwards on this one. I know you don't want to do 25, but it's like the e to the u problem we were doing earlier, if you ever want to look at that. So you said 27 to look at next?
Yeah, sure.
Okay. So this was early on in the course here.
Sorry, how do you know for the last one to do a right-hand Riemann sum?
Yeah, okay, I'm glad you asked. You don't know because the question doesn't tell you. It's either a right or a left, and I don't know because it doesn't say. It should say right or left.
Oh, okay.
It's like there's another answer where it's sine 0 plus sine 1 over 30 plus sine 2 over 30, where it stops at 29 over 30. And then it's a left, but we don't know until
Okay.
then.
So like both of them are right then? I like if you did a left hand, how do you know that you got the wrong answer?
It should say right Riemann sum. Then this wouldn't be a question. Like I think
Got it. Okay.
I think
It would say.
yeah, your question is valid because it's not we're not being fair to the student. If you and I are writing a test and you brought that up, I would say, well, you're right. So we should either clarify or give a different, say this is the right sum, this is the left sum. I don't know.
Okay, got it.
Okay. All right, so this one says, which of the following is true? So the first is the limit as x approaches 1. So you do that by just plugging in the numbers. It's 3 times 1 squared minus 5. Does that equal question mark 6 times 1 plus 2? So this is 3 minus 5. Are these the same?
No.
So that doesn't exist. Now, how about at the derivative? So now we got to find f prime of x. So that's 6x and then 6. And then you do the same thing, the limit as x approaches 1.
Yeah.
6 times 1 equal to 6. And that's odd, but that's possible. I mean, so yes, that works. And then f prime of 1 is the last thing. So f prime of 1 is, well, so you would use the top one because it's less than or equal to.
Wait, f prime.
Because the top one is valid at 1.
Why do you have to do f prime of 1? Didn't we just do that with the left?
No, we already have it. Like the derivative, we already have it, I guess. Since this is the derivative, you have to know which one to evaluate it at. And because it's at 1. Yeah.
So it's 6. And then
yes, it does exist. Because the limit from the left is the same as the limit from the right is the same as at that actual value.
Oh, they're asking you to find out. I wasn't looking at the paper, that's why I was confused. Okay. So it would be, it wouldn't be differentiable, right? Because it's not
It's not continuous.
right. And differentiable or no.
You're right. I'm sorry. It's not continuous, so it can't be differentiable.
Right.
Even though the derivatives. So I was about to tell you it was 2 and 3, but it's only 2. Sorry, what were you gonna? I interrupted you.
True statements. Wait, but f of 1 does it? Why does it not exist?
Because it's not continuous. Because at one it's like, let's think of a really simple graph. At 1, so here's 1. Here's the slope from the left, and here's the slope from the right. Do they have the same slope?
Yeah.
Yes, but they don't touch, so they're not.
Oh, okay.
It's not differentiable. That's what it's trying to show you.
Got it. Okay.
And then you're like if it's continuous, well, if it's differentiable, then it's continuous, but not the other way around. Differentiable means it's continuous.
Okay.
But the other way, not always.
Right. You can't go from, yeah. Yes.
All right, let's look at 28. Okay, so g of -4 says d dx integral 0 to -4 root t squared plus 9 dt.
So you do the antiderivative t squared plus 9, right?
Well, okay. So if we go back and we just do this, if we ignore this for a moment and we just do this part, what this says is put x in here, multiply by the derivative of x, which is 1. Okay, but then you got to take a derivative of it.
Why?
I'm sorry. We did the derivative. I'm sorry. That is the derivative. I'm sorry. This is one of the fundamental theorem of calculus, which is the derivative of the integral means to put that in and multiply by the derivative.
Okay.
And so this is g of x. G of x literally is.
Oh, so then you just plug in the
Yes,
-4.
Yes.
So then -4 squared 16 plus 9. Oh, okay. So root 5, yeah. Okay.
All right.
I
Well,
have to go through and review all those cosine, sine.
Yes. Yes, you have some motivation right now, I guess, because boy, you're right at the end of the year. It's got to
be so hard.
Yeah.
All right.
All right. Well, I know we got something scheduled for tomorrow, maybe the next day. So thank you for scheduling. Look forward to helping, and I'll send you the notes here shortly.
All right. Thank you.
You're welcome. Great night. Bye now.